Hi everyone. Today I'm happy to present our paper, Programmable and Adaptive Scheduling for Distributed Systems. Scheduler is a crucial component in all distributed computing frameworks, responsible for assigning tasks to appropriate nodes in a cluster. The fine-grained execution of modern application workloads, such as LLM serving and streaming video analysis, create a high-throughput environment which highlights the importance of efficient and high-quality scheduling. However, scheduling policies today are typically hard-coded in distributed computing frameworks, which leads to two problems. The limited expressiveness prevents supporting new policies, and a fixed implementation cannot adapt to workload changes, resulting in poor application performance. To better understand the pain point, let's go through a concrete example. Here, we are showing a scheduling policy which combines dominant resource fairness and load balancing, aiming at fair resource allocation across users, while also distributing tasks evenly in the cluster. The first step is to enforce fairness. The scheduler will look at the per-user dominant resource usage and select tasks from the user with the lowest usage. The second step is load balancing, in which the scheduler assigns a selected task to the least loaded node in the cluster. Although it is a quite common and simple scheduling policy, prevalent frameworks fail to specify it due to limited expressiveness. Moreover, there are many ways to implement the policy, and the best choice is workload and environment dependent. Inappropriate implementation will lead to poor application performance. Let's dive more into the second point. Here I'm showing you three possible ways to implement the DRF-LB policy in terms of the logic execution position. The centralized version on the left contains one scheduler instance handling all tasks in the cluster. In contrast, the decentralized version on the right has multiple scheduler instances, each seeing part of the tasks and independently making decisions. The middle one, which we called the hybrid implementation, split the logic into two stages. All the tasks go through the centralized scheduler to enforce the fairness rule. Then, the selected task will be forwarded to one of the decentralized scheduler to execute the remaining load balancing logic. There exists trade-off in scheduling throughput and fairness between these implementations. The scheduling throughput goes up from centralized to hybrid to decentralized as more and more logic are scaled out, and this directly leads to increased application throughput. In terms of fairness, the centralized and hybrid implementation can provide strong guarantee as they can have the complete information of all the tasks. However, the decentralized version may violate fairness requirements as each scheduler instance can only see local tasks, resulting in potential starvation. We run experiments on these implementations under various task incoming rates to evaluate throughput and Jane fairness index on service ratio, and the results here empirically demonstrate the trade-off. Different implementations should be chosen on different rates to maximize throughput while satisfying fairness requirements. Unfortunately, existing frameworks choose one implementation under all circumstances, which miss the opportunity of utilizing the advantages of different strategies. It is worth mentioning that the choice of implementation goes beyond logic placement, which also includes how to implement submodules, such as making trade-off between immediate probing and periodical heartbeats for remote information retrieval. Therefore, adaptive implementation has the huge potential of improving application performance. To recap the problem, hard-coded scheduling in distributed frameworks has two issues. The limited expressiveness prevents writing new policies, and the non-adaptive implementation hurts scheduling performance, which directly leads to application performance degradation. Therefore, we argue that policy specification should be decoupled from underlying implementations based on two principles: high-level programmability and adaptive execution. Developers should be able to express diverse policies in a concise, framework-agnostic manner, and the system should adjust the implementation strategy based on current conditions, including workloads and network environments, to optimize performance. Achieving this vision requires addressing a few interesting challenges. The first challenge is about how to design a programming abstraction that is concise, expressive, and can facilitate adaptation analysis. The second challenge lies in intelligent adaptation. Given this policy specification, the system needs to find the most appropriate implementation, which requires comprehensive reasoning on various metrics. The policy specification is a pure mathematical description with perfect information and zero overhead. But in practice, scheduling throughput limit and processing delay are inevitable. And because information are scattered due to the distributed nature of underlying systems, all implementations more or less deviate from the original semantics. For instance, the centralized version of DRFLB is not perfect, as the load information is either probed via network requests or periodically reported from the nodes. Both of them leads to staleness. Also, the decentralized version suffers from partial view, as each instance can only see local tasks. Semantics deviations result in suboptimal scheduling decisions, which leads to diverse consequences, such as increased application latency, fairness violations, or more resource consumptions. Therefore, a unified representation is needed to quantify semantics deviations in order to analyze implementation trade-offs. We propose a compiler-based approach with a domain-specific language as frontend. The core abstraction of our DSL is the scoring function, where developers encode their desired policy as a score for every task node pair as potential decision, and the pair with the minimum score will be chosen. We provide a number of hooks throughout the task lifecycle to enable specifying scheduling information maintenance. As shown in the slides, the DRFL build example can be expressed with around 10 lines of code, and more details are available in the paper. The scoring abstraction allows us to define semantics deviation as the comparative ratio on scores to an omniscient scheduler with perfect information. Specifically, we collect and replay the trace of tasks to estimate the ideal scheduling decisions and concrete implementation decisions respectively. And then, we compute the comparative ratio on scores using these two groups of different decisions. Closer to 1 means smaller deviation, and vice versa. We allow developers to set up a comparative ratio threshold to filter out unqualified implementations. We evaluate this method on the fairness metric we mentioned before. The dashed lines shows the changes of comparative ratio, which share the similar trend to the changes of GFI in the solid lines, indicating that it is an effective guidance for the compiler to estimate semantics deviation. In conclusion, hard-coded scheduling is problematic due to limited expressiveness and poor performance. Therefore, we argue for programmable and adaptive scheduling. We propose a DSL with scoring abstraction and intelligent adaptation via comparative ratio analysis. Thank you.